Okay, let's dive into this. Welcome to The Explainer. Today we're unpacking a puzzle that literally sits at the very foundation of how our modern physical world is built. It's a challenge that designers and engineers have wrestled with since, well, the dawn of the industrial age. And honestly, mastering it changes absolutely everything about how we build the physical objects around us. To really wrap our heads around this, just picture an airplane wing. Think about what that wing actually has to do, right? It's got to be incredibly strong. Strong enough to carry literal tons of structural load, passengers, and cargo through turbulent skies without snapping. But at the exact same time, that very same wing has to be incredibly light. Because if it's too heavy, that plane is never leaving the ground. So stop and ask yourself, how on earth can one single physical thing be extremely strong and extremely light at the exact same time?
Well, our basic human instinct tells us that achieving both of those things simultaneously is just impossible. Think about it. If you want something to have more strength, what do you naturally do? You add material. You make it thicker. But the second you make it thicker, it inevitably gets heavier. The two properties just fight against each other. This right here is the absolute signature contradiction of mechanical engineering. It's this instinctual barrier that feels like an unbreakable law of physics.
This brings us to Section 1, the trade-off trap, classical engineering's endless compromise.
We see this tension everywhere, whether you're designing a car chassis, a robotic arm, or even a high-performance bicycle frame. And look, lightness isn't just some cosmetic preference or a fancy design buzzword. In the physical-mechanical world, every single gram of weight translates directly to performance and ultimately money. More weight means more fuel consumption, more energy required to get that object moving, way higher overall costs, and slower motion. If you can solve the weight problem, you unlock immense value.
So how does classical engineering usually handle this dilemma? Well, they rely on what I like to call the classical engineering scale. On the left side, you want more strength, but you're forced to accept more weight. On the right side, you want more lightness, but you absolutely have to sacrifice your strength. To gain on one side, you have to give up on the other. And honestly, brilliantly talented engineers spend their entire careers just trying to delicately balance these two competing sides of the scale.
But here is the major turning point. What if you don't need to balance that scale at all? What if you can just break it? We don't have to accept this traditional, endless compromise. What if we could look at this contradiction not as a permanent balancing act to manage, but as a specific, targeted problem that can actually be completely solved?
Let's move into Section 2, the catalyst, TRIZ, tapping into humanity's memory of solutions.
If we're actually going to break that scale, we need a massive paradigm shift. And that shift comes from a system called TRIZ. It was created by a brilliant researcher named Genrich Altschuler, and he did something absolutely incredible. He studied tens of thousands of patents across completely unrelated industries, and he noticed something profound. The exact same contradictions, like our weight versus strength problem, kept appearing over and over again, whether it was in aerospace, automotive, or everyday consumer goods. Altschuler realized that by creating a common language for these repeating contradictions, we could look at our specific mechanical engineering problems in an entirely new way.
Now, what's really interesting about this slide is how we translate our problem into Altschuler's common language using his contradiction matrix. On one axis, we have what we want to improve, the weight of a moving object. On the other axis, we have what we must not harm, its strength. At the exact intersection of those two parameters in the matrix, you don't just find a blank slate. You find the specific inventive principles that thousands of successful engineers before you have actually used to solve this exact same tension. So here's the absolute crucial point. You are not solving from zero. When you use this matrix, you're tapping into humanity's accumulated memory of engineering solutions. It gives you the exact direction of the solution, so you don't have to rely purely on random trial and error, or just, spontaneous, unstructured brainstorming. The heavy lifting of finding the core principle, it's already been done for you. That leads us to Section 3, separation in space, changing the question entirely. When we look up our specific weight versus strength contradiction in that matrix, one of the most powerful inventive principles that hands right back to us is something called separation. And this requires a really crucial mindset shift. The wrong question, the one that keeps us permanently trapped on that balancing scale, is asking, should the part be light or strong? The right question, guided directly by the principle of separation, is, where should it be strong, and where can it be light? You see, physical parts don't carry a load evenly across their entire volume. When a part is under stress, some regions are absolutely crushed under that load, while other regions of the exact same part are honestly doing almost no work at all. Let's see how this builds into a real, step-by-step, inventive logic. Step 1. Identify the regions of high stress in your part. Step 2. Identify the regions of near zero stress. Step 3, and this is the real magic, put material only where the stress is high and ruthlessly remove it everywhere else. Do you see what happens here? We aren't balancing the contradiction anymore. By separating the properties in space, we dissolve the contradiction entirely. The part becomes super strong exactly where it needs to be and incredibly light everywhere it doesn't.
Which brings us to Section 4, the perfect shape, the I-beam explained through TRIZ.
Let's ground all of this theory in a concrete, everyday physical reality. And this brilliantly illustrates the concept sitting right in front of our eyes. Think of a standard structural I-beam. It has thick flanges at the top and the bottom and a very thin web right in the middle. When a beam bends under weight, the stress highly concentrates at the top and bottom surfaces, but the stress is nearly zero right in the dead middle. So, the I-beam perfectly applies the separation principle. It keeps the heavy material at the highly stressed edges and completely hollows out the useless middle.
Now, I'm not saying the I-beam was originally developed explicitly using the TRIZ methodology, but its design can be perfectly explained through TRIZ. And once you understand the principle of separation in space, I promise you, you start seeing it applied in the wild absolutely everywhere. The structural I-beam, hollow drive shafts in vehicles, incredibly strong honeycomb panels used in aerospace, they all use this exact same logic. They all brilliantly separate the contradiction in space.
So what's the ultimate result here? The contradiction wasn't balanced. It completely disappeared. We didn't just manage some sad trade-off. We didn't accept that adding strength strictly requires adding massive overall weight to the object. No! By using the TRIZ principle of separation, we bypassed that instinctual barrier entirely and achieved both incredible strength and incredible lightness, simultaneously.
And remember, this isn't just a fun, intellectual thinking game for designers. There is massive, real-world commercial value here. A new geometry created this way isn't just a neat idea. It becomes a protectable invention. It literally becomes a patent. Turning these stubborn engineering contradictions into highly valuable intellectual property assets is exactly why mastering this kind of structured, inventive thinking is so critical for modern engineering.
So, I want to leave you with this final, provocative question. What unbreakable scale or contradiction exists in your own work right now that you could absolutely shatter? Stop balancing the compromises that everyone else in your industry simply accepts. Look for the underlying contradiction. Apply a structured system like TRIZ to tap into humanity's past solutions and figure out how to make that contradiction completely disappear. Thanks so much for joining me on this explainer, and keep questioning those instinctual barriers.